We'll have an exam next Friday. This Friday. This Friday. Yeah, me too.
Didn't we do
Monday? Yeah.
Okay, that's more useful.
Yeah.
I'm gonna be out of commission this Sunday, and be honest.
Why?
Football.
Oh, you see that? I thought you guys were playing.
Last game.
Here?
Home. No, not to home, it's away. Where's it at? Outland. Yeah. If it was closer to my home, I might have
So I forgot completely that we had the exams. Oh, I need to make that. I need to prepare an exam. Oh, I'm moving.
We'll give you more time to prepare. It's okay, you can do that.
Yeah. Okay, no, I put a homework for electronics when I put this one. Let me share the screen. Okay, so I hope it is a shorter class today. What we're gonna try to do is just keep working with this concept of magnetic vector potential, and just try to do a couple of problems of how do we use it, how can we obtain the magnetic field from the vector potential, so on. So it's very similar of if we have the electric potential, then we can go and find the electric field, and then we can find polarization and stuff like that. It's going to be something similar. We're going to have a magnetic vector potential, and then from here we can calculate a magnetic field flux, and from here we can calculate the magnetic field. So that's more or less, and we can do back and forth. So that's pretty much the objective of what we're trying to do today. We're going to do some problems that involve a little bit more integrals and stuff, and some other ones that I think are really simple. And we're going to do the basic case. It's basically calculating the vector potential magnetic vector potential for a finite wire at a point P. Okay, so I'm going to have a wire. This wire is going to have a current, and I'm going to assume that this current is going to be constant. And I'm going to place this wire on along the z-axis. So I'm going to do it with red. Okay, and I'm going to have a point P here. And I'm going to say that that point P is going to be along the x-axis. Okay, and this is a finite wire, so I'm going to say, okay, this wire is going to go from Z1, all the way to point Z2. And the distance to point P, this is just going to be a distance A. Okay, so to calculate A, one way I can do is by integration. So if we have the current distribution, when you have current distributions, then you can calculate A by integrating mu over 4 pi r, and this is the current dl. Okay, here my current is going to be in the Z direction. Oh, well, yeah. Oh, yeah, no, sorry, this is just a constant. This is just going to be a constant. dl, this line differential is going to be z dz. So you can imagine that I'm going to take a small little segment of my wire. Sorry, I'm going to take a small little segment of my wire, and and this is going to be my r, the distance to my point P. So this dl is going to be a differential z along the z-axis in the z direction. So it's going to be z hat to dz. Okay, and this r, the magnitude of r is just going to be the square root of a square z square. Okay, so from here I can calculate a. There's going to be an integral. It's going to be a line integral, and it's going to go from along the length of my wire, so from point 1 to point 2. I'm going to have mu naught I dz of 4 pi a square c square, all that in the z direction. Okay, these first three terms, 4 terms are all a constant, so I can take them out. So I'm going to have mu naught I over 4 pi, and then this is going to be the integral of c1, c2, dz a square c square in the z hat direction. Okay, I'm actually kind of lazy. I think we have done this before. I think we did it when we started talking about magnetic fields. We did this integral. I'm going to use one of the tables of integration. So this will be equals to mu naught 4 pi natural logarithm of c plus c square plus a square from c1 to c2. Okay, and then just evaluating those limits and those integral, those limits of integration, then we're going to have that this magnetic vector potential is going to be mu naught I over 4 pi natural logarithm of C2 plus C2 square plus A square in the C direction. Yeah. Now, once you calculate A, once you have A, you can calculate your magnetic field flux. And we can calculate that using the curve of A. Okay, now I'm gonna write down the whole curve. And so this will be this row direction to this direction.
That's in the book.
Huh?
That's in the book.
That's in the book. Okay, so I have here my magnetic vector potential, and my magnetic vector potential only has components in the z direction. I don't have any components in phi or rho. So these terms, I'm going to be using this later. So these terms, this one, and this one are gonna be zero just because I don't have that A component. So the only thing that are gonna be using are the components of A, that partial derivatives of the Z component. Now this is the partial derivative of Z component with respect to phi, but this one doesn't have any dependency of phi, so that's gonna be zero too. So this is gonna be zero. So the only one that I'm gonna be using is gonna be this. Okay, rho, this line of integration is the distance from my line to my point P. So I'm going to be integrating with respect of, I'm going to rename this A to rho. So I'm going to have mu naught I for pi, and then I'm going to have partial derivative with respect of rho of and the derivative of x of x, this is 1 over x, the derivative of x. No. 1 over g dx. Okay, so before you fall asleep, try to do this integral, this derivation, sorry, this derivative of the argument of this natural logarithm. And that's going to be in the z direction. Yeah, you guys got it? So we're gonna have mu naught I over 4 pi, and then we're gonna have what? C2 square plus rho square over 2 pi, 2 rho, minus 2 rho. Yeah. This is going to be in the free direction, and this is going to be my magnetic flux. Nico, you falling asleep?
1 week left.
1 week off, sorry.
Deprivation.
Yeah, so you can simplify this a little bit. You will have over 2 pi of but that will give you your magnetic flux. Yeah, so this is just a different way to calculate this magnetic field. We have done, I think, this problem 3 different ways. We use Biot-Savart, we use Gauss law, and now we're using magnetic potentials. At the end, you end up with a very similar equations, maybe expressed a little bit different, but it represents the same thing. Yeah, makes sense? Okay. So now we're going to do the opposite thing. Like we are going to have a vector potential and we want to find out the current density. So what we did was, given the current density, calculate the vector potential. Now, given A, what will be the current density? So what will be the current density? In order to produce magnetic vector potential A equals to K phi, where K is a constant. And we need cylindrical coordinates in this case. Okay, so we have A. I know there's going to be this thing, K in the phi direction. And I want to know, okay, what is the current density? What will be this J current density that I need in order to produce this magnetic vector potential? So this is in 2 parts. So the equation that I can use to calculate the current density, that's going to be the curve of the magnetic field flux. That's going to be mu J, that's Ampere law. And I know that I can calculate B from the vector potential. So I know that okay, so I need to get the curve of this. That will give me B. Then I will do again the curve, and I can use that to calculate J. Okay. Okay. So I'm going to be working with cylindrical coordinates. So this will be the curve. Okay, so look at this value of A that I have, K phi, and then just calculate the curve of A. Yeah. You calculating?
No, I'm looking at it and trying to figure it out. I'm a little confused, but.
Es pasa. No, it's not going to be C. Because that implies that then the magnetic field is going to be zero, and then your current distribution also going to be zero, so you won't have a magnetic field.
So, that's a bird, so. Just the first one.
Yeah, no, so you have A only has to play in 5, right? And K is a constant, so. So this is going to be 0 because.
That's fine.
Yeah, this is going to be 0, this is going to be 0, this is going to be 0. All those are going to be 0 just because we don't have any components in rho and z. So the only terms that we're going to be using are the ones that have phi on it.
Okay,
Yeah?
that's what I was debating between whether it was.
Yeah? Everybody got a value for B? Not yet? So this one is also going to be 0 because we don't have any dependency on Z. So the only one that we need to is going to be this one, right? So we're going to have one over rho in the C direction. Okay, we're going to have that. So I'm going to do it explicit. So I'm going to have 1 over rho partial derivative with respect of rho k of rho k in the C hat direction. So that's just going to be k over rho in the C. Okay? Yeah, so k phi, your vector potential is in the phi direction. Now this is going to be a magnetic field that's going to be in the z direction.
I thought that it was it was K, P. I didn't see the
Oh, no, no, no.
direction.
Yeah, it's a k in the phi direction. Ah, that's what you got it done. Okay, now calculate the curve of B. Now B only has k over rho in the z direction. So you're gonna have the, oh, you're only gonna have the C component. So you don't have any row component, it's gonna be zero. Because you don't have
Okay,
any dependency. This is just direction.
yeah. I
So,
was thinking, you know,
but raw, you can have a dependency on raw. This one depends on raw, right?
yeah, that's right, yeah.
But not C,
Yeah.
this one doesn't depend on C, only depends on K and raw.
Okay, so it's just that. Oh, okay, that was just that.
Is it just that C?
Yeah, so we have K over raw in the C direction, okay? So we only gonna have, you can think of it as we're only gonna have a component in Z, which is K over raw. Okay, so this is gonna be zero, this is gonna be zero, this is gonna be zero, this is gonna be zero. Because all these depends on phi, this are the phi component or the rho component. So because we don't have any, they're gonna be zero. We only have the Z component. So we're gonna have this term over here, but because it doesn't depend on phi, this is still gonna be zero. So the only thing that is left is gonna be this guy. The negative partial derivative of Z with respect to rho. Okay, and this is going to give us what? Minus K over rho square in the phi direction. Yeah, and I know that this is going to be equals to my current density times mu naught. So from here I can find J. Okay, ish. Okay, we'll do one more. I'll let you guys. Well, you guys are dying here.
Yeah, I wish I could get more than 4 hours of sleep. I keep my medicine on the last 4 hours, and I'm up in the middle of that.
The what?
I'm not coughing.
Oh,
Whenever I lay down straight, whenever I lay down, for whatever reason, my lungs don't like it, and I'm just still a little bit sick. What? That's a deep cut. But, yeah. My roommates love it. I wake them up at like 5 a.m. You know, I had the weather paper and then 6:30.
6:30.
And
For
football.
why you guys have meetings at that? Well,
Because the class is at 8. So. Yeah, we do that in the spring. But usually we start at 6. So then we get breakfast and like Yeah, we got a little bit more time.
That's what, like, all right, meeting starts at 7:30, good luck.
Okay,
Oh, yeah.
Cartesian at least. Okay, now prove that B is a magnetic field.
Proving it would be a magnetic field, we should be finding like that it's not equal to zero.
Yeah, I think so.
Mm-hmm.
Yeah.
So remember that the divergence of magnetic fields are always going to be equal to zero. So if you calculate the divergence and it's not equal to zero, then it's not going to be a magnetic field.
I'm gonna start with dot zero, cross is zero.
Correct. This is a dot.
What for electric?
Hmm.
What's for electric field?
The curve of the electric field is zero. I'll bring more obstacles next class. The spicy ones. So you can wake up a little bit.
I'll make sure to sleep.
I forgot the gum.
I go, I just thought that I'd be like, have like a cough shot or something.
Yeah, so this one is pretty straightforward. We have Cartesian coordinates, so it will be just partial derivative of respect of x of dx plus the partial derivative with respect of y of dy plus the partial derivative of c of dz. And here we don't have any cross dependency, so all of them is going to be zero. Okay. Now, calculate the charge density, the current density. That one, this one is a little more complicated.
No.
I'll write down so. Yeah, I guess here it will be y square, c square, x square.
Something like the order in which you do it.
Uh,
I just have to look it up every single time.
So the way I do is, okay, you're gonna do the X component, you're gonna cover the column and the row, you cover it. So you're gonna end up with, you're not gonna have those four terms. So these two are gonna multiply minus this term. And then for the next column, the one has a negative sign, you know? So again, I'm gonna cover this and this. So this column is row, and then I'm gonna have this term, minus this term, and this term. Then, and the last one, the same thing. The only thing is that you need a negative sign for the what, when you do the what components. That's the formula. Yeah, it's not there, but it has the formula has one.
Okay. Yeah, that's pretty good. Okay, thank you.
Does that whole thing is multiplied by the amount as well?
Well,
Or is that part of the cross somewhere?
no. So that expression that you got, that's going to be equals to mu, not j. So if you want to calculate j, you will have to divide by mu. What?
I think I have the right answer.
You got the right answer?
I think.
Good.
I'm probably wrong, but.
So I have the x components, I'm going to have negative 2z
Okay.
minus the y components, I'm going to have two x, and then in the c component, I have negative 2y. Yep. So the current density will be negative 2 zx plus xy plus y in the c direction over mu naught. This is z. Okay, make sense? Let's stop here. I'm gonna let you guys leave a little bit early, but I think you guys need a break. It's too much stretch.
I am so glad that I scheduled 2 classes each day.
Normally it's manageable.
Next semester?
This, where it's just,
No, I have Jensen. Break my streak of having Rigetto as a professor.
No, you have had Jensen before, right?
Yeah. I had a streak of like 4 terms with Jensen.